An astronomy meeting, we've got a stellar performer, and I think that we can all agree that, having heard Alan's talks in the past, he is indeed a stellar performer in these sort of audiences. So Alan's going to give us a talk about unlocking the secrets of near-Sun comets. Alan Fitzsimmons.
Thank you. Thank you, and can I just start off by thanking the BAA Comet Section for inviting me here today. As you've noticed, I've actually been here all day because I just love looking at comets like a buzz. Can we swap those lights back, please? Oh, what you want? No, I don't want a photo. I want you guys to see the screen. Thank you. You can have a photo later. I believe it's sunny out. Okay, start again. I would like to thank you, as I said, for inviting me here today. As I said, I was here for the first time 3 years ago talking about, I believe it was Pan-STARRS, a project that I'm still involved with. But when I was growing up in the old little market town of Newbury down in Berkshire, I used to hear about this thing called the British Astronomical Association. Never actually thought I'd be here at a meeting of the Comet Section, and of course because of that I've never actually joined, so there you go.
There's homes at the back.
But on to today's presentation. I'm going to talk to you about comets, which I've really kind of had an interested in for a number of years, but only really started looking at seriously actually since my last visit to you here. In 2014-2015 I was a member of something called the Near-Sun Comet team. This is a bunch of international team, I should say, of cometary scientists that was actually put together by Geraint Jones down at MSSL/University College London. To actually say, well, look, we've been observing comets whose perihelion distances, closest distances to the Sun, are really close. And we've been seeing these things for years, but what do we actually know about them? And more importantly, what things don't we know about them? And so we met once a year for 2 years. So just 2 meetings, but we had a lot of email traffic between us, and we produced a review paper on the current state of knowledge on these things. Because it turns out, of course, that when you look back in the records, some of the brightest comets ever seen from Earth have been comets that pass close to the Sun. If we go back to one of the most famous ones, the Great Comet of 1680, I think we've already seen this picture of the comet over Paris on the left-hand side. It reached magnitude -10 to -11 by some measurement. I'm not going to revisit that talk. But it was one of the most famous ones, of course, because it was the comet that Newton used as the frontispiece to the Principia Mathematica. This is a picture I took of one of the 2 copies in the Royal Astronomical Society a couple of years ago, and you can see how he's traced out in this case, the fitted parabola of an orbit to the path of that comet, showing it as it goes through the system, or the inner solar system. Now, there have been other, as I said, very bright comets. Today is a beautifully sunny day. What would happen if we went out and looked up in the sky today and saw that? The Great Comet of 1853 by Charles Piazzi Smith, well known for other reasons in astronomical circles, but not a bad painter, it turns out. And this is what it looked like when it was at perihelion by eye that day. As you can see, from the Cape, from near the Cape down in South Africa, and yeah, pretty good. Later on, here it is over the skies of Paris. And that was a pretty good one. Possibly about magnitude -10. And it turns out this is a second source of inspiration for me, because that comet is actually in a kind of reproduction I've had hanging on my wall in my house for a few years. I've got this reproduction, and so actually it's not a very good thing. It's something called Astrofest down in London, but it's not a BAA thing, so you won't have heard of it. It's not that successful. But here we go. Here's the comet and the zodiacal light, and I've reproduced what it says on this engraving from 1843, as seen from the terrace of the Maison Guigla at Nice on the evening of 17th of March 1843. And the two things you notice about this picture, of course, is A, they've got very dark skies in Nice back in 1843, because that's the zodiacal light there. On the right hand side of the picture. Secondly, it may be March, but it's still pleasant enough down in the south of France to walk around in your normal clothes after sunset, so there you go. Almost as nice as Northampton. Carrying on, the Great Comet of 1882, and now we move from engravings and paintings to photographs. Magnitude -15 to -20, possibly. Let's always remember that. But these, of course, are possibly the earliest photographs of a comet in existence. And in fact, it was these photographs of 1882, amongst others, which convinced astronomers that this new invention of photography could be used to catalogue the sky, and acted as the kickstarter, in today's parlance, of the Carte du Ciel, and the great photographic surveys from then on of the night sky. Now, let's jump forward about a century or so, not quite a century, to Comet Ikeya-Seki. And I like this because this is the first one in my slideshow where I was actually alive. Just. That's right. October 1965, magnitude again, -10 to -11 at perihelion. Is a beautiful picture on here from Roger Linds. I think this must be before the dawn sky, after perihelion. But here's this beautiful picture using a ground-based chronograph of the comet within an hour of perihelion. So we had known for centuries that there exists a group of comets whose perihelion distances, their smallest distance between their orbit and the Sun, is incredibly close, about or within one solar radius of the photosphere. Then we move to space, because there were, in the 1970s, the Solwind satellite was sent up into orbit, and when they started observing the Sun, it was the first attempt at observing the corona, the outermost atmosphere of the Sun, with a remotely operated space observatory. They saw this thing coming in on 31st of August, and for weeks they thought it was a problem in the optics. Until somebody realised, no, what you've got here is a comet heading towards the Sun. Now, we are quite almost blasé about this because of one particular satellite, the Solar Orbiting Heliospheric Observatory, or SOHO, launched in the mid-1990s. It's not actually in orbit about the Earth. It's at the Lagrangian point between the Earth and the Sun, where, due to a trick of gravitational dynamics, we have a local minimum in the gravitational potential. So if you put it in what we call a halo orbit, it just stays there. And slowly orbiting there, basically about 1.5 million kilometres, or 100th of astronomical unit sunward of the Earth, continuously monitoring the Sun 24 hours a day. And it really is a fantastic mission, now up there for over 20 years. And what SOHO has seen, well, apart from the Sun and boring things like that, are comets. It has seen thousands of comets heading towards the Sun. Now, this is a sequence of images put into a movie using the chronograph on board SOHO. I generally, when I'm playing these movies, I loop them. So here you can see the sunlight being blocked out. you can see a circle which shows what the apparent size of the sun would be in these images, if you can see them. And generally, coming up from the south, you'll see, well, in this case, not one but two comets approaching and disappearing behind the occulting disk. SOHO was launched with 3 coronagraphs. One, the innermost coronagraph, failed very soon into the mission, but the other two, the remaining 2 are still operating today. So if we go from the C3 coronagraph to the C2 coronagraph, the innermost inner coronagraph here, one can see in this loop, we can see if the comets are coming up here, you'll see them coming in here and disappearing. As I said, the spacecraft has been returning these images, which are freely accessible on the internet, and they are typically searched by amateur astronomers for comets. You can do this yourself. There's free software. You download it. You can download the last bunch of data, and you can process them and look for things that are moving. Now, some of the things that are moving will be stars, of course. If you look down here, you can see, particularly down here, you can see over this sequence the stars moving behind the sun, because of course SOHO is keeping track with the Earth as we orbit the sun. But if you see something not moving in that direction, it's got to be something other than a star. So far, there have been over 3,200 comets detected in SOHO images. And when you look at the rate, when you correct for observer biases, sometimes the spacecraft has been down for one reason or another. There's roughly 1 every 32 hours heading into the sun. That's quite a few. And just to prove it, I took a look at some data yesterday. No, actually, I was in Milton Keynes yesterday. Sorry, it was Thursday when I was at home in the evening, and I started taking a look through. And yeah, here we go. So I went to February this year, and I picked kind of a nice one. And here we've got a frame that was taken at 21:32 on the 7th of February this year. I'll start playing the movie. I made this little movie. What I want you to do is watch this red line going here, because what you'll see is not just stars in these frames, you'll see lots of speckles coming and going. These are the cosmic ray hits on the detectors, because the detectors are in deep space. They're not protected from all these usual cosmic ray hits by the Earth's atmosphere, as we do on ground-based telescopes. But apart from that, what I want you to do is watch above this line, and if you look very carefully, you should be able to see towards the bottom of that arrow now a comet heading in towards the sun. And you see it gets, well, not too shabby, but then it starts fading and disappearing, and I'll come back to that in a minute. Well, this is the modern view of the so-called sun-grazing comets. It was actually over 100 years ago that it was recognised that many of the brightest comets that had orbits associated with them, even elliptical orbits, were these so-called sun-grazing comets. Comets that passed generally about within one solar radius, or 700,000 kilometres of the solar surface, 5/1000ths of an astronomical unit. It was also noticed that many of them, and we'll come back to this in a minute, many of them have almost exactly the same orbit. They're different comets, but they're following, as far as we can tell, almost exactly the same path around the sun. And if you see 2 or 3 of those, you have to wonder if that's chance. If you see 3,000 of them, you know it's not. We believe that these are probably fragments of an original, well, there's no other word for it, monster comet that split up sometime in the past. And we call these comets Kreutz Sungrazers after this chap. Now, we saw some moustaches in an earlier presentation, but I think this gets the prize today. Heinrich Karl Friedrich Kreutz was actually, despite his military photograph here, quite a good astronomer. And he was the first person to realise that many of these comets coming through, that had been seen, many of the bright comets, were following the same path. They were part of a family of comets. What could cause this family back then of a few bright comets, now for over 3,000 fainter comets? Well, there's one thing we know that can do it: tidal forces. All of these comets pass close enough to the Sun that if we assume that there's very little strength in a comet, you can almost pull it apart by its bare hands, then you don't even need to pull it apart yourself. The Sun's gravity will do it for you. It passes within something we call the Roche limit of the Sun. And we've seen this happen before. The most dramatic in my lifetime, in my studies, is when we all had fun back in 1994 watching the 21 fragments of Shoemaker-Levy 9 plummet into the planet Jupiter. But there were 21 fragments because 2 years previously, unobserved from Earth, the progenitor object had passed within the Roche limit of Jupiter, and Jupiter's gravitational field had split it apart, tidally disrupted it. To show how dramatic the Kreutz catalogue is, let's take the orbits of every single comet we've ever seen. I've plotted these in a kind of funny way. Here on the x-axis at the bottom, it's the perihelion distance. How close does the comet get to the centre of the Sun? Or rather, how close does the comet's orbit get to the centre of the Sun? We start out 100 astronomical units, where there aren't any because we just don't have telescopes that are sensitive enough yet. Then we go through to 10 astronomical units, 1 astronomical unit, 0.1 astronomical unit. So basically, all our planets are between about 0.3 and 30 on this plot. I've had to plot it logarithmically. Then we go to 0.01, and the dashed line shows where the Sun's visible surface is, the photosphere. If you're going in closer than that, you're not coming out again because you've hit the Sun. Now, on the y-axis, to spread this plot out a bit, I've used the inclination of the comet's orbit. That's the tilt of the orbit, of course, relative to the Earth's orbit. If it's at 0, it's orbiting in exactly the same plane as the Earth. If it's at 90 degrees, it's going at right angles. If it's at 180 degrees, it's actually going backwards in the Earth's orbit, and I've got no idea why I plotted up to 200 degrees, because that's impossible. But there we go. So we've got a whole bunch. We've got thousands of comets on here. First of all, we've got the long period comets. These comets out here, mostly we see in the outer solar system, although there's a smattering of them that reach into the inner solar system. And these are the comets that we believe have come originally from the Oort cloud. And they come in at all directions. And that's why they have all random inclinations, going from 0 degrees to 180 degrees. Then, down here, we have the Jupiter family comets, or the short period comets. These are the comets that we believe have come from the region, the trans-Neptunian region, outside Neptune. And in fact, funnily enough, now I was going to say the Kuiper Belt, but we don't actually believe that what we think of as the Kuiper Belt is where these have come from. Current dynamical theory actually is implying that they come from a separate class of objects out there called the scattered disk objects. We then have objects that certainly get close to the Sun, but not quite as close as a Sungrazer. We call these sun skirters. They get within 100th and a 10th of an astronomical unit. And you'll notice there are clumps. All these comets have very similar orbits, implying that, again, they were originally one larger comet that has been broken up through either a splitting we've heard about, maybe major outbursts that we heard about as earlier as well from Richard. And then finally, up here, we have the Kreutz family. Now, one thing I should point out at the moment is that it looks like this clump is quite tight, but there's some kind of spread in it. Don't believe that. We see, if we're lucky, we see these comets for 6 hours. From entering the chronographic field of view to disappearing. And that ain't long enough to get a good orbit. And I'm sure many of you understand that. So it could be that all of these are incredibly similar, or it could be that spread is real and it tells us something about how the original progenitor comet was broken apart and had different velocities that were near the sun. We simply don't know because we cannot trust the orbits. The other thing is that sometimes people call the Kreutz Sungrazers comets hitting the sun. No, they don't hit the sun. As far as we can tell, all of these have perihelion distances above the photosphere, about 100th of an astronomical unit. Possibly this guy over here is the only one that almost definitely would have hit the sun if it had reached there. But even then we're not sure. Brian Marsden wasn't sure, and if Brian Marsden isn't sure, I'm not going to question him. But when did then this giant comet, this monster comet, come around? When was it in the sky? When could you have gone out after sunset? Hopefully it was a clear night. I live in Northern Ireland, so I would have had to move somewhere. But maybe, when was this monster comet around? And when would you have seen this, I don't know, magnitude minus 20 or something stupid comet on the horizon? Well, here's one guess. There's a report, and this was one of the first attempts to do this. This was from Brian Marsden back in 1967. There was a bright comet around in 326 AD. And maybe it split up because there were other bright comets that were seen within a few years of each other, which, if we call them superfragment 1 and superfragment 2, were around in 1100 AD and 1106 AD. And then they possibly split up into some of the great comets that we've seen, and then they split up as well. Actually not when they were going around the sun then, but you see, the other problem is that we don't even know the orbital periods of the Kreutz family comets. We don't. The orbits are not good enough. So this could be the kind of family tree, and maybe the original comet was around in 326. Or maybe not. Here's another possible family tree published by Paul Chodas and Zdenek Sekanina back in 2012, where now with the original comet comes around in 467 AD, because yep, somebody reported a bright comet then. So there you go, and then you come up with some possible idea, putting in delta ejection velocities splitting velocities between the fragments and cascading fragmentation far from there. Look, nobody knows. Okay, this is the point I'm trying to get. We can make educated guesses, but they're educated guesses. We don't know. And it's a shame, because let's show you what we know of what happens in the inner solar system because of SOHO. The geniuses at NASA's Scientific Visualization Studio have taken all the comets. Now, they've been very picky. They've just taken the comets seen by SOHO, i.e. any comet that enters the field of view. Now, that could be a Kreutz Sungrazer, or it could be a normal Jupiter family comet, just happens to pass through the field of view, or it could be another comet coming in from the Oort cloud. And let's see what happens as we play time forward from the beginning of 1996. The red dots coming to the sun are the Kreutz Sungrazers. Cyan and purple dots are the sun skirters from the other groups. There's a few Jupiter family comets coming around that you would see, and Halley-type comets, but look at these red comets coming in. We're now up to the end of 1997. They're not stopping. They're just going to keep going and going and going. And this is happening now. If we went to the SOHO data site now, and I won't because I've got a few more slides to show, then there's a significant possibility we would see a comet heading towards the sun in those data. And, well, yeah, I could keep this going for another 15 years, but I'm not going to, because I don't want the timer to beep. So, SOHO's doing a great job. Oh, look at them all coming now. Oh, dear. What chance does an amateur astronomer have to discover the next great comet coming in? Well, quite high at the moment, because although I'll warn you, notice that this is a view from looking down on the solar system. The inclination of these comet orbits are all such that they come in from the southern hemisphere. Unless the comet's bright enough, you can see it near the sun, near perihelion. We don't stand a chance in the UK of seeing any of these guys, I'm afraid. If you're in the southern hemisphere, people like Terry Lovejoy can discover them for a few more years. Certainly, I think until the year 2022, 5 years' time, the next bright sungrazer would have a proper name, not Pan-STARRS or Catalina or something like that. But at that stage, if everything goes to plan, and I'm afraid, sorry folks, but it is on track, here's the construction site yesterday from the webcam down in Chile, we will have the Large Synoptic Survey Telescope operating. The UK is a partner with that. Myself and some of my team are working on this right now. We're preparing for the largest discovery rate of solar system objects in history. It will only be, it is in the southern hemisphere, so it's not going to be doing much of the northern hemisphere. This shows a map of the sky and where it will be showing. This is the entire sky on the right hand side, and you can see if you look at the green, which is where most of the survey work will be done, this shows that pretty much it won't go far above declination 0 in its surveys. It won't go above that really, apart from doing a bit of mapping along the galactic plane and also what we call the North Ecliptic Spur, because we want to discover stuff in the solar system that it aren't comets as well. We want to do those boring asteroids that you've heard about. More of those later. But it is an 8-meter telescope. It will have an almost 10 square degree field of view. It will reach a limiting magnitude of almost 25 in 30 seconds. It will do that once a minute. It's planned to cover the entire southern hemisphere once every 4 nights. And so, although it will not see any comets near the sun, because it will never do a survey shot below 45 degrees altitude, just to maintain the image quality for much of the science it will do, it will be able to see Kreutz family comets a long way out on the way in. So there will be a lot of comet LSSTs starting in 2022, and like most surveys, that will ramp up. So that's all kind of fun now. We're kind of giving ourselves up and basically buying more disk drives. But at the moment, we still have bright comets discovered by amateurs, and of course one of the most famous ones in recent years was Comet 2011 Lovejoy, reached magnitude -3, the Christmas comet in 2011. Here's a beautiful picture of it by Colin Legg on the left hand side. If you wanted a really nice view though, you just have to look out the window of the International Space Station. And actually the story is, I don't know if this is true or not, but the story they say is that they weren't actually warned about this comet, and they were watching the sunrise over the limb of the Earth and went, "What's that coming up?" That searchlight. And yeah, that was Comet Lovejoy. Comet Lovejoy was amazing for us because of course we did follow it with SOHO. Here it is coming into the SOHO field of view on the 14th of December, and I've put together this little movie showing how it approached the sun. The amazing thing is that by this stage we had other solar telescopes operating, and so we didn't know. We thought it would break up because again it's going to approach within the Roche limit, and indeed it did break up after perihelion, but it survived going around the sun, because here it is coming back out again. The flashing, by the way, is just different exposure lengths saturating the CCD camera. You can see the remains of the tail over here. It looks like it's still heading into the sun, but it's actually being blown away by solar radiation pressure. With things like the Solar Dynamics Observatory, you could actually see it shooting through the inner corona, just above the photosphere. These are beautiful. Now, be careful interpreting these things. This is taken through a filter designed to image the hot ionized gas lying just above the photosphere in the inner corona, above the chromosphere and the photosphere. So I think this is probably ion 14 or 7 or something like that. So you're looking at gas that's several 100,000 Kelvin, or actually degrees C, Fahrenheit, it doesn't matter at that stage, right? And so what you're seeing here is you can't actually see the comet itself as it shoots through, But what you're seeing is the material released from this comet immediately ionized. Electrons are ripped apart from it, and that's what you're seeing in here. Point out that when it was going around perihelion, this comet was going at 0.1% of the speed of light. It's that fast. Another cool thing, though, is something I've avoided talking about till now, is that we see these comets going in, we very rarely see them coming out. And let's have a look here. Here's another selection of that movie of Lovejoy going in, and you can see the different exposure times gives you this kind of funny effect here. But let me play the movie a little bit, and you'll see that when it comes from behind the sun, there's not much of a tail. It's so hot, as soon as the dust is released, it's vaporized. It's over 1,000 degrees. And here's the great thing about being in the BAA Comet Section. You put anything that close to the sun, everything becomes a comet. And this is actually how we know a bit more about these Kreutz Sungrazers that the SOHO spacecraft sees going in all the time. Because here's a typical light curve that we see from one of these Kreutz Sungrazers. This was SOHO comet number 517. And the chronographs have two filters, a kind of a greeny blue filter and an orange filter. It's just broadband filters. In the green, you see, the typical behaviour you see is that you see the comet getting brighter and brighter until it reaches somewhere between 10 and 20 solar radii from the centre of the sun, and then it starts dimming again. If you can follow it long enough, you'll see it getting brighter again. We think there's a secondary thing going on there that we still don't quite understand. We also see that generally the comet is brighter in the orange filter than the green filter. Now, first of all, why is it doing this kind of shape? It's because when it gets to about there, it's pretty much gone. Everything is sublimating. We're used to thinking of ice as sublimating, turning into gas on normal comets in the inner solar system. Here, rock, dirt, anything is going. Nothing is surviving at this distance. And so effectively here you're running out of comet to vaporize. This secondary peak here, we don't quite understand. It may be a secondary ionization effect, because the thing is these are broadband filters, and we're not sure what kind of emission is in there, because we've never got a spectrum of one of these things, because there's no spectrograph from the chronograph. But one thing we kind of believe is that because the orange filter is always brighter than the green filter, and orange contains sodium emission lines, we think this may be due to the sodium, although it can't be just due to the sodium because the numbers don't work out. There'd have to be too much sodium, so we're not quite sure what's happening. But we see these peaks in the light curve, and we think there's sodium emission, and this light curve is what tells us the size of the comets. Because when we get to here, when we add up all that light, that's everything. That's everything gone. Everything vaporized. So add up all the light, try to figure out what the spectrum is, the reflected spectrum light, and say, what, how much material is there? And it turns out that we believe that most of these comets coming in have radii only somewhere between 10 and 50 meters across. These are really small bodies. They're much, much smaller than the typical comets we all observe out there. They're bright because you're vaporizing everything in them. Now, you might say, well, that's crazy, but it's true. Look here, these are theoretical curves that calculated by Matthew Knight a little while ago now, showing if you start off with a radius of 10 meters, 20 meters, 30 meters, 40 meters, and 50 meters here on the right-hand side of the plot on the right-hand side of the slide, this is how the size goes as the comet moves into the sun. And when you reach a radius of 0, the horizontal at the bottom, you've got no comet left. And nothing above 50 meters, nothing below 50 meters can survive in one of these orbits. But how do you get so many comets? Well, that's the thing. I'd like to take this moment in the talk to thank you for inviting me not to talk about Comet 67P. So here's a picture of 67P. But I don't want to okay, it is a glorious thing, isn't it? But let's take a closer look at the surface. Here's the region of the neck between those two lobes, the head and the body of the nucleus 67P. We're looking at just over 300 meters across in this shot. And look at these boulders. These, if you let them into an orbit and put them into a Sungrazing orbit, would become a SOHO Kreutz comet. Out of even a small nucleus like 67P, you could easily feed many more times comets than we have seen so far with SOHO. So actually understanding how many there are is not a problem now, because we knew beforehand we could do the calculation what kind of volume you're looking at, but when we got the 67P we had absolute proof. You can take these boulders, throw them into a Sungrazing orbit. These things we would see in SOHO. So we know a lot about these Sungrazers, these near-sun comets, but there's some important questions. What are the true orbits of these small comets? We don't know. We've got some idea of the larger ones, and they do show a dispersion in orbital elements, but we don't know about the smaller ones. And if we could get them, then we might understand more about how this original progenitor split up, may even be able to narrow down when it was around. And does fresh ice exist on near-sun comets at the surface orbit depth, or are we just seeing a devolatilized husk from when it was last around, when it broke up from the parent comet? And more importantly for astrophysicists, and something that we're really curious about, what happens when you take a comet and throw it within 100th of an AU of the Sun? How does its surface change? How do the chemicals and the compounds on the surface change? We have no idea. And the problem with this is that we've never seen one of these small comets before perihelion. And this was something I really suddenly understood going to these meetings over in Switzerland. So me, Colin and Matthew Knight decided, let's do some observations. So I produced a model where I took the catalogued orbits and said, okay, let's assume that these objects have some activity or not, and how bright are they going to be as seen from Earth on their way in to the Sun. And the first thing you realise is that if there are no ices and they're inert as they go in towards the Sun, before they start vaporising, we stand no chance of seeing them with any telescope now or planned. But if they're active, then as they go in from the Sun, there's this on this plot now I'm looking at distance on the sky from the Sun against total magnitude here. You see that as we get built to 90 degrees from the Sun, they're still at like magnitude 23, 24. But as we get to 60 degrees from the Sun, they're up to maybe 21st magnitude. We're starting to have a chance of getting them. So that's the first thing we did. And a year and a half ago, or a year and a bit ago, we used this telescope. Now, here's a picture I took of the telescopes on the platform, what we call the platform at Power Now. So you've got four very large telescope units here, four 8.2 meters, that's unit 1, unit 2, unit 3 is just behind here, stuck behind unit 4. But there's this guy over here, which people tend to forget about. This is the VLT survey telescope. It's a 2.5 meter diameter telescope with a wide field camera on it that gets you 1 square degree at a time. So in January, actually it says January 2015, that's wrong, sorry, it's January 2016. We surveyed 27 square degrees over 9 nights to magnitude 21.5. Basically, it had to look really low down, and it only could observe for an hour before it started getting too bright, because the sun was coming up. So we went there and we spent a lovely January getting these data and looking through them quickly every night, and we didn't find any. Boo. So we still haven't found one. We've got a proposal, and we've got a proposal to repeat it. We're not convinced we're going to get the time, because basically even if everything goes well, we only increase this, go up from 27 square degrees to about 70 or 80 square degrees if we follow our new observing plan. But nobody else can do it, so that's what we're going to try and do. But we could tell this was going to be hard, so we decided to make things a bit easier for ourselves. We decided to, let's forget about the Sungrazers and go back to the sun skirters. Because some of those sun skirters have been around the sun more than once while SOHO's been there. And because they're periodic, we know the orbit a lot better. And so this is the object that we initially decided to target. It was first seen in 1999 by SOHO, P1999R1. Orbital period 3.99 years. Perihelion distance, you see the perihelion distance it's really small, but not as small as a Sungrazer, so we call it a sun skirter. So it gets with 0.05 astronomical units of the sun. Here's the orbit on here. Now, again, we had never seen this comet outside of the SOHO chronographs. We only knew it's periodic because every 4 years a comet came around and it had the same orbital elements in terms of fitting an ellipse to those positions as 4 years previously. So you kind of know. I mean, it's the same thing that Halley did, and he got a comet named after him. And oh look, there's only 3 of us, and 3 is the maximum number of people you can have on a comet name. So anyway, so we'd seen it, as I said, at that stage in 1999, 2003, 2007, 2011. Here it is. So another SOHO movie. Here's the sun blocked out. Want you to look above the red arrow, and as I play the movie, we should see, there it is. Just coming up there, gets bright, and then it starts fading away again. It's because actually perihelion is there from our vantage point. We're kind of skewed in our vantage point from the Earth. I'm repeating the movie, so there it is again. And we'd seen that 4 times. Here's the Lightcurve from 2011, showing the similar kind of behaviour you had before. You get a peak, then a second peak, but we know it's not vaporised. It doesn't get as close as the normal Sungrazers, and we had seen it 4 years in a row. So the likelihood is that it would still be there. We also believe that it must be at least 100 metres across, because if it had been 50 metres across, it probably would have disappeared over several orbits. So we applied and got time on the Very Large Telescope to try to find this comet. Here, to scale, is the comet orbit. Goes around once every 4 years. Here's the Earth's orbit. And here's the position of the Earth and where the comet should be on the 22nd of May. 2 years ago, 2015. It would have been 1.1 or 1.2 AU from the Earth, 2 AU from the Sun. So quite a way out from the Sun. But we thought that we should be able to get it. We applied to use this. Here's the VLT UT1 with it's quite a nice camera and spectrograph on board, but we're just using the camera in this case, the Force 2 camera, and this is me standing next to the camera underneath the telescope. The actual mirror's up here. This is just the instrument cage below the telescope. The Force 2 is nice because it gives us a relatively large field of view for the Very Large Telescope, 8 arc minutes by 8 arc minutes. And we worked out, and it's quite easy to do, that even if it was as faint as 24.9, in 230 seconds we could detect it. Yeah, it's strange working with 8 metre telescopes. They collect a lot of light. It's weird. But here's our problems. It was going to be moving 2 arc seconds a minute. That's not okay. We can track at 2 arc seconds a minute at a Very Large Telescope. It's built to be able to do that. We don't know the real brightness. We were hoping it would be brighter than 24.9 because there's a lot, when you go down to that magnitude, there's a lot of stuff in the sky. But we didn't know how bright it's going to be. Here's the real problem. It was going to be in the Milky Way. Another problem, we weren't quite sure where it was going to be. Remember, we did have a really proper orbit. We just had the observations from SOHO every 4 years, well, 4 times, plus the fact that it had an orbital period of 3.99 years. So when we put in the application, we had an uncertainty region on the sky, but that's this big oval here. And it's about 1,000 arc seconds across, so what's that? That's over 10 arc minutes across. Actually about over 15 arc minutes across, a bit shorter. But that was okay because this shows the field of Force 2. the size at which we could survey, and clearly we can just maybe survey, put it there, integrate, eventually something we hope will pop up. Even better was that originally when we proposed the Jet Propulsion Laboratory only had the positions from up to 2007. We then contacted Carl Battams, who's also on the near-Sun Comet team, and he measured the astrometry and submitted it for the 2011 apparition, and that shrank the uncertainty region down to there. So brilliant, this is not going to be hard. We had a whole 5.4 hours on VLT to do this. Yeah, you have to calculate exactly how much time you need with VLT. With JWST it's going to be a nightmare. Anyway, so that was it, and so we were all ready to go. And I went down there, arrived there 2 nights before the observations, got set up, and then did a really stupid thing. I said, well, this is the JPL orbit. Let's just double check that the Minor Planet Center has an orbit that matches. So that's where the Jet Propulsion Laboratory says the comet will be. Where does the Minor Planet Center say it will be? Now, let's get this right for a minute. According to JPL, there's a 99.7% chance the comet's in this region. So what's going on here? I'm not going to go into that right now. So with the 48 hours to go, had to quickly rejig the observing plan. But it's okay, we had 5 hours, over 5 hours in the VLT. I can do it. Here's the fields that I can go, and because I'm now uncertain exactly where this damn thing's going to be, I'm going to extend it a bit out there and a bit out there just in case. I don't know where this thing's going to be. So we're going to find it. Now, the nice thing is that we're going to be doing this near the middle of the night. So the first 2 or 3 hours on the telescope we'll use for another program. I had my camera, so I thought, wouldn't it be nice to have a record of what we do if we do find this object? So basically, just before I started observing, I went up onto the platform without my light. Okay, without a torch, and set up my camera on a tripod. I decided to take a picture, and actually just take loads of pictures and let the camera keep going on automatic mode until the batteries ran out. So, here's the movie of us searching for the comet, and you'll know when we find it because we'll stop and go back a bit. There we go. Right. And I literally lifted it. I got it at sunrise. I went and picked up. I knew the battery would be dead, and that was it. So yeah, we did find it. We found it in field 1. I didn't start at field 1. We actually started at field 8. Yeah, but that was okay. We had to because the comet was moving, and basically if we started in field 1 it was over a dense patch of stars at that time, but by the time, if we started at field 8, by the time we got to field 1 would be over a nice little bit of dust cloud in the galactic plane, so we'd get clear, and it's here. Here's half of the frame of the exposure. So we've tracked at the expected rate of the comet, the stars are trailed, and okay, look, you're not going to see it. There it is. It's up there.
Close to the edge.
Yeah, but we got it. So, let's zoom in. There it is. Single exposure. Easy. It turned out to be easy with VLT. Immediately in that frame we could see it's magnitude 22.5, plus or minus about a tenth of a magnitude.
Didn't we see the other one?
Diameter about 550 meters. Fine, and in fact, because we found it and because there were new astrometry from it, Minor Planet Center actually gave it a number, 322p SOHO. We also had follow-up time. If we found it, we also had other time for the 16th of June, 12th of July to go off and observe it again. We didn't have to go down that time because we knew where the comet would be. We could just do the surface observations. Also, Matthew Knight had the 4-meter Discovery Channel telescope. We could just about get down there, and he had time during June as well to try and see it. And anyway, we basically observed the heck out of it on the way into the sun, and we found some interesting things. So first of all, here's this is a co-addition of 35 minutes on the VLT. Down to so we're going down to 30-something magnitude per square arc second. There's nothing there apart from the point source. I can tell you, there is nothing there apart from point source. This streak is a residual from the star track going past that, which for some reason didn't come out, but there is nothing there. no dust cover. So on the way in, it wasn't active. Then, of course, during these observation periods, we also got the colours. Now, these may not mean a lot to people, but I can tell you right now, because, when I'm not talking about comets, I'm talking about asteroids. These aren't the colours you expect for a comet, but they do look like an asteroid. But maybe it's due to the intense heating of the surface, or the inherent nature of the body. Remember, we don't know what passing a lump of ice and dust that close to the sun does to the surface. That's okay, because Mike Kelly was on board this, and Mike, just point out one other thing. Mike could get another telescope involved. Before I talk about that, here's the light curve from our VLT data set. Here's the apparent magnitude. It's a function of time. Looks like we've got a rotation period about 2.8 hours, and that's a problem. Because if it's a comet, you can't spin that fast without breaking up, because they're basically effectively strengthless. It's not very elongated. We can tell from the maximum minimum how elongated it is. It's even going by about 30% from spherical, but it can't spin that fast and be a comet. Then Mike comes in. Mike gets Spitzer time. We had Spitzer. If we detect it from VLT, the Spitzer time will kick in. So Mike used the Spitzer Space Telescope to detect the thermal emission from it. And here it is again. Here's from May 22nd of VLT as Discovery images. Here it is in July 24th as it's close to the sun from Spitzer at 4.5 microns. Now, because we don't know where in the light curve we are, we don't know what the albedo is. But basically, the range of probable albedos is higher than typically known for comets. It also tells us the size is between about 300 metres and 150 metres. So the question was then, is this really a comet? And this is why I admit to you, folks, that I've been living a lie in this talk, because Comet 322P is not a comet. It's a near-Earth asteroid. Many near-Earth asteroids become near-Earth asteroids because they enter mean motion resonances, or something called secular resonances, in the asteroid belt. Once they're in those resonances, it only generally takes about 1 or 2 million years to go from a near circular orbit to an orbit where the eccentricity is near 1. And it doesn't matter where you are in the solar system. If the eccentricity is near 1, that means that perihelion, you get really close to the sun. And in fact, if I was going to plot the position of 322P on this plot, it would be there. 322P is just a near-Earth asteroid, something that's been predicted but never seen. It's a near-Earth asteroid that is near the end state. It's going to end its life, not by hitting a planet, not by being ejected from the solar system by Jupiter, but probably by being completely vaporized by the sun. So, that's 322P. Oh no, we haven't found a comet. Let's chase another one. 323P, SOHO, sun-skirting comet. Again, pretty similar. 0.048 AU perihelion distance. So again, about 10 times further out than the Sungrazer. Orbital period a little bit longer than 322P. 323P is 4.2 years. Again, seen 5 times to SOHO. We, earlier this year, 23rd, 26th of January, me and Matthew Knight went out to the INT. It's a picture of me. I did this just as the moon was setting, so you could see the INT against the sky. And we went and observed. We've got a wide field camera. It's not as sensitive, of course, because we've only got a 2.5 metre telescope here, but we do cover 1/4 of a square degree, basically the size of the full moon on the sky at any one time. And indeed, now this time, instead of watching for the comet going in, we're going to watch for the comet going out. So we had this time in January, so it was good in November last year to see the comet coming out as expected. Here it is. 323P SOHO. Just in case you weren't convinced, what I've done, I actually did this yesterday, took the data and did difference in imaging. So basically I've subtracted a kind of background image from the sun just to make sure that you can see the object back in November coming out from the sun much more clearly. There it goes, just again above the red arrow. So we went off. We had not bad weather. It was a bit dodgy on the first night. The second night was clear, beautiful. Third night wasn't bad. Fourth night was okay, but we had this sky at night TV crew in the bloody control room if you saw that, what was it, the February episode. So anyway, yeah, so we're looking in this region for you, all of us who actually do know the constellations. Zoom up, this shows how the CCD detectors look on the Isaac Newton telescope. And this is kind of reached, I think this was night 2 or might be night 3 or night 2, this particular field. The thing's moving now. This one, we were going to look at it because it's coming out from the sun and it would be relatively close to the Earth. It was moving at over 3 arc seconds a minute. But anyway, we would go off, we banged away with the thing, and here's one of my images. So this is about an hour and a half imaging on the Isaac Newton telescope. We've got a field here because I've dithered around to fill in the gaps between the CCDs, between the individual detectors. I've got 42 arc minutes across here. And just to prove we are going deep enough, we predicted that this thing would be fainter. We thought it would be fainter than 322p, even if it was inert, but it would probably be not fainter than magnitude 22.5. So if we zoom in to that combined frame with on the stars, we can see that we're certainly getting down. Well, that's really bright at 21.8. That's a bit fainter at 22.7. There's 23.06. We are definitely getting down to 23.5 in the combined images, because these frames are 1 minute exposures, so they're trailed by 3.7 arc seconds. And of course we're tracking the comet, so the comet won't have that trailing. That gives us another 0.3, 0.4 magnitudes depth. Anyway, so that's right, we got the data. It's fantastic, and it's not there. This shows the field from one of those nights, and again, this shows the 3 sigma uncertainty ellipse, according to the Jet Propulsion Laboratory, of 323p. By the way, the minor planet center position is also about here. Again, it's a bit off, but it's definitely in here as well. I should have put it on there. And it isn't here. So, 1 success, but as it stands right now, 1 failure. We don't know anything more about this comet. We're kind of almost hoping that in 4.2 years' time, SOHO won't see it, which meant it has vaporised entirely, and that's why we didn't find it with the Isaac Newton telescope. At least it would give us an excuse. But when we because we don't know where it is, we can't use something like Spitzer for it either. So all we have to go by is the fact that we didn't see it at that particular time, and if it was there, it was magnitude fainter than 23.5 in slow R. So here's the curve, telling you how the upper limit to the diameter as a function of what the actual albedo is of the object. If it's a really dark object, then it could still be 200 meters across. It was darker than any known comet. If it was a comet with an albedo of maybe 0.04, then we're looking at something 90 or 100 meters diameter. If it's not really a comet and we've been conned again by the universe and it's an asteroid, end-state near-Earth asteroid, then we'd expect an albedo, a reflectance, somewhere near the right of this x-axis, and if we bring up to the line, that would mean that the maximum size is only 50 meters across or whatever. So we don't know. We're actually we're going to do this properly, and so because we're all very busy, because we're senior professional astronomers, we're going to get a student to do this, but we're going to get somebody to plough through this data again, just in case, although we've already done it twice. Let's get a fresh pair of eyes on it, but we don't think it's there. So here's my summary. Most sungrazing comets that we see are fragments of a previous giant monster comet, whatever you want to call it. 2 small Kreutz Sungrazers vaporise approaching the sun roughly every 3 days on average. So again, think about it. Spend 3 days looking at SOHO images, on average you'll see 2 comets going into their doom. And those are comets because we believe they are cometary in nature. We haven't seen, however, any of those small Kreutz comets from Earth because it's just difficult. They are small, and on the way in, you've got to, even if you're in the southern hemisphere, you need to look pretty low down, close to sunlight. Sun skirting 322p turns out to be not a comet. surprisingly, it's an asteroid. That becomes cometary because when you get that close to the Sun, everything's a comet. And we didn't find 323P in January this year, so failure. What's next? We're kind of getting interested in what does happen to objects when they get really close to the Sun. So we've started a program of observing, first of all, near-Earth asteroids, with asteroids at least with very small perihelion distances, and also clearly something to do here. So actually, I've said 2018, isn't 96P around at the end of this year? 2017. I have to check that up. We're going to study 323P, sorry, that's a mistake. 322P, because it comes around every 4 years, and in 2019 it'll be back again, and this time we're going to get a spectrum. And get a better light curve, and anything else that VLT and ESO will allow us to do in this. But it was a good paper, we think we've got a good chance of studying this again. And all I can say is the next great sungrazer that you can see by naked eye could be discovered tomorrow, and for at least for the next 5 years, maybe by an amateur astronomer. Thank you very much for your attention. Oh, and one last thing, just to, okay, bullet points, never leave bullet points on a PowerPoint slide. I couldn't find, I'm afraid to say, a pretty picture. Well, there are loads of great images. A pretty picture of a comet from this part, a great comet from this part of the world. So, just south of here, though, here's a painting of Dynamical Comet from Oxfordshire by William Turner in 1859, and that's kind of nice. Thank you.
Thanks, Alan.